We are being pulled by the Great Attractor. Imagine a hidden mystery in the huge space around us, an object so powerful that it's tugging everything, even our galaxy, toward it. It's like a cosmic magnet, and we call it the Great Attractor. This force is so strong, equal to the pull of 1,000,000 billion suns. Now you might be wondering, what's going on out there? Why is this happening? It's like a space puzzle that scientists are trying to solve. This incredible thing, the Great Attractor, is about 250 million light years away from us. That's a crazy distance. People have been studying and guessing about it for a long time, but there's still so much to uncover. What exactly is this mysterious force, and how does it affect our journey through space? Before we dive deeper, hit the subscribe button and turn on your notification bell so you don't miss out on any of our videos. Beginning as early as the 1970s, astronomers noticed something peculiar going on with nearby galaxies. Sure, there was the expected Hubble flow, galaxies drifting due to the universe's expansion. All the nearby galaxies seemed to be dancing to the same cosmic beat, converging toward a mysterious center stage. Astronomers debated whether this was a real effect or some artifact of Malmquist bias, the bias we get in our observations because bright galaxies are easier to observe than dim ones. For fans of statistics, it's just another expression of a selection effect. It could be that a complete census of the nearby cosmos, including the much more numerous small and dim galaxies, would erase any apparent extra movement and return some sanity to the world. But then came more detailed observations of the cosmic microwave background. The CMB is the leftover light from when our universe cooled from a plasma state and formed neutral atoms when it was a mere 380,000 years old. A relative infant compared to its present 13.77 billion years of existence. This glow, known as the cosmic microwave background, cloaks the entire universe, making up almost all the light we see. But with some careful observations, we can spot a subtle difference. It's a bit warmer in one direction and a bit cooler in the opposite direction. Now you may be wondering why temperature twists. Well, that's because of Earth's cosmic stroll through the universe. As we move ahead, the light coming towards us gets a bit bluer, and the light coming from behind gets a bit redder. By measuring this color change, we can figure out our speed, roughly 600 kilometers per second, pointing somewhere toward the Centaurus constellation. It's like the universe is giving us a gentle nudge, letting us know we're on the move. We can easily account for some of that motion, as the Sun is orbiting around the center of the Milky Way galaxy, and our galaxy itself is headed on a collision course with our nearest neighbor, the Andromeda Galaxy. Those combined motions account for some of the 600 kilometers per second, but not all of it. It appears that we and almost all the galaxies around us are barreling towards some random spot in the universe, compelled to move against our will by a distant and unknown source of immense gravity. Now rewind to the late 1970s. Astronomers were busy mapping out the vast universe, uncovering a stunning cosmic tapestry known as the cosmic web, a beautiful arrangement of galaxies. But here's the catch. There's a mysterious area in the sky dubbed the zone of avoidance. Why the mystery? Well, our galaxy is dust central. Big clouds, small clumps, and random particles. This cosmic dust creates a celestial fog, making it challenging for astronomers to see what's going on, especially when it comes to the secrets of the Great Attractor. Since most of those early surveys operate in visible wavelengths, the Milky Way is like a cosmic fog machine, blocking our view of galaxies beyond its edges. This is the zone of avoidance, a cosmic blind spot in our otherwise thorough surveys, a place where we can't quite see what's happening. Imagine a secretive region in space where the mysterious Great Attractor hides. For the longest time, we were in the dark about what was happening in that part of the universe. The structure, the identity, and the contents of the Great Attractor were all a cosmic puzzle. Astronauts had stumbled upon something there, hinting at a discovery tied to our movement through space. The catch? We didn't know the full story. Now, astronomers are left with two options. The first option was to sit back and wait for our solar system to casually spin around the Milky Way, hoping for a better look. Sounds simple, right? Well, not exactly. It turns out that would take a whopping 100 million years, a bit longer than your typical grant funding cycle. So as you can imagine, that wasn't the most practical solution. The second option was to get creative. Never once to let a celestial object go unobserved, astronomers turned to other wavelengths of light to peer beyond the dust of our galaxy and into the depths of the universe. In the quest to unravel the mysteries surrounding the Great Attractor, scientists employed the powerful tool of X-ray light, renowned for its ability to cut through cosmic dust. However, its revelations were limited, offering glimpses of only the most luminous galaxies actively birthing stars and the exceptionally large yet rare clusters of galaxies. Enter the hero of the cosmic exploration saga, infrared. Unlike its X-ray counterpart, infrared proves to be a versatile champion, capable of peering across vast distances, a feat spectacularly demonstrated by the James Webb Space Telescope. Picture the 1990s as the era when astronomers initiated a grand cosmic scavenger hunt, armed with both X-ray and infrared surveys within the elusive zone of avoidance. This cosmic pursuit is no stroll. It's a rigorous cosmic quest that demands an immense investment of telescope time. Each sweep of the telescopic lens unveils only a handful of galaxies or clusters, making it an intricate and time-consuming endeavor. While the maps are a work in progress, they're already painting the initial strokes of a comprehensive portrait of the universe's region anchored around the Great Attractor. Think of it as turning on the cosmic lights in a room that's been shrouded in darkness for a long time. The combined efforts of X-ray and infrared surveys are like illuminating the hidden corners of the universe, revealing the intricacies of the celestial landscape centered on the enigmatic force known as the Great Attractor. Now let's journey from our cosmic doorstep to the grand neighborhoods of the universe. Picture our home, the Milky Way, as a vast expanse stretching across 100,000 light-years, adorned with hundreds of billions of twinkling stars. And just next door is Andromeda, a colossal galaxy residing a whopping 2.5 million light-years away. Throw in Triangulum, a smaller galaxy often overlooked, along with a bunch of dwarf galaxies, and you've got our stellar community known as the Local Group. What makes our cosmic connection even more fascinating is that thanks to gravity, we're all interlocked in a celestial dance. Fast forward a few billion years, and we'll witness a spectacular cosmic waltz as we emerge into a colossal megagalaxy. Now, here's where it gets even more captivating. The Local Group, our cosmic crew, is on the move as one cohesive unit. Our destination is the Virgo Cluster. The Virgo Cluster, known as the bustling metropolis of our cosmic neighborhood, is located approximately 50 million light-years away. Imagine this cluster as a bustling city of galaxies, with over 1,000 individual galaxies packed into a relatively tight space, forming a ball about 5 million light-years in diameter. The Virgo Cluster is a heavyweight champion in our celestial vicinity, boasting a mass of over 1 billion trillion solar masses when you add all of its stars, gas, and mysterious dark matter. The Virgo Cluster and the surrounding groups also form what's known as the Virgo Supercluster. Unlike clusters and groups, superclusters are not gravitationally bound and have not yet completely collapsed. Astronomers once thought that the Virgo Supercluster was the largest structure in the nearby universe, but more extensive surveys within this zone of avoidance have revealed the true scope of the picture. The Virgo Supercluster is but one branch of an even larger supercluster known as Laniakea. The Laniakea comprises 4 supercluster branches totaling over 500 groups and clusters with more than 100,000 individual galaxies. The massive tangled complex stretches for over 500 million light-years. But before you get lost in what we're discussing, let's take a step back about 13 billion years to understand the Great Attractor and why it's at the center of the Laniakea supercluster. Back then, our universe operated like a cosmic construction project. In the early days, about 13 billion years ago, things were pretty uniform. No big density gaps. However, gravity, though weak, played the long game. It grabbed onto tiny density differences, working gradually over hundreds of millions and then billions of years. If you look at the cosmic microwave background, you'll spot tiny temperature differences, 1 part in a million, revealing the initial density variations. Here's where gravity's relentless work kicks in. The rich density regions get richer, pulling in more material, while the poor lower density regions get poorer. Over time, this process shapes our universe. Low density areas become vast cosmic voids, and high-density spots evolve into stars, galaxies, and even superclusters like Laniakea, with the Great Attractor at its heart. It's like a cosmic game of accumulation where gravity is the master builder. This large-scale construction project is still underway. Galaxies and clusters formed billions of years ago, but gravity is still at work, piercing together superclusters including the Great Laniakea. It's like a patient builder, pulling on cosmic Lego pieces to create stable, settled structures held together by gravity. When we talk about the Great Attractor, don't picture it as a thing, but more like a place, a hub of gravitational attraction. It's the downturn of our cosmic neighborhood, the ultimate place everyone is heading toward. This gravitational hotspot is the result of billions of years of slow construction, the grand finale of our cosmic project. It's not just where we happen to be going, it's where we've always meant to be headed, our cosmic destiny. Despite it being our celestial downtown, it remains a destination forever out of reach, adding a dash of cosmic mystery to our journey. Scientists are still figuring out the Great Attractor's exact makeup and location. We can only infer its mass and location based on relatively sparse surveys within the zone of avoidance and reconstructions of the movements of those galaxies, which is slightly difficult because we can't watch anything move in real time given the enormous scales involved. Now, the supposed location of the Great Attractor already contains an immense bunch of mass known as the Norma cluster, which is located over 200 million light-years away. Our own Virgo cluster and all its surrounding galaxies are on the move toward Norma, which sits at the center of the flow of all the galaxies within Laniakea. But here's where it gets interesting. Norma isn't sitting still. It's moving toward another supercluster called the Shapley supercluster, potentially bigger than our own Laniakea. This hints that Norma at the bottom of our local gravitational well might be part of an even deeper cosmic well nearby. And wait, there's more. Another supercluster, the Vela, unrelated to the Great Attractor, also plays a role in our cosmic motion. It's like the universe has a few surprise twists up its sleeves in our cosmic journey. Unfortunately, all of this is temporary. Gravity's great engines of creation shut off over 5 billion years ago, leaving the cosmic web forever incomplete. The fugitive is dark energy, the mysterious troublemaker of the cosmos. While we don't grasp what it is, we know it's accelerating the universe's expansion. Over time, any galaxies that are not already gravitationally bound to each other will find themselves flying apart at ever faster rates. Dark energy has always been here in the background. Early on in the universe of the cosmos, the combined gravitational pull of all the mass in the universe was enough to overwhelm the accelerating effects of dark energy, allowing gravity to build large structures in peace. But 5 billion years ago, things changed. The matter contents of the cosmos diluted too much, allowing dark energy to take hold. Our local group will survive the coming expansion annihilation, but Laniakea will not. We will never even reach the Virgo cluster, let alone the site of the Great Attractor. Slowly, over the next few billion years, our motion toward the Great Attractor will slow, then stop, and then reverse. What do you think? Let us know in the comments below, and don't forget to like and subscribe to our channel for more updates.